Okay, thank you for the introduction, and thank you to the organizers for organizing this event and for the opportunity to speak. I'm happy to be here, and today I will tell you about hydrodynamics with dipole conservation. So we'll continue in this theme of hydrodynamics, and this presentation. Well, by the way, you don't see the bottom? Oh wait. Okay, the slides is cut. 1 second. Good. Oh, do you see? Oh, now you see it. Okay. Now you see it. Good. Okay. Okay, so this presentation will be based on the two publications that we have done together with Piotr Sodówka and Francisco Peña Benitez. Okay, so this research was motivated by the so-called fracton phases. And so what are fractons? Fractons stand for excitations of fractionalized mobility. So what we mean by that is that an isolated fracton may be unable to move in isolation, or maybe it's only allowed to move in certain directions. And they were first discovered in exactly solvable lattice spin models. One model that is I recommend that you check is the X-cube model. The details of this model are not so important, but what I would like to tell you about this model is that it has just some lattice model, has local interaction, and it hosts this excitations of fractionalized mobility fractons. And on top of that, it has this very exotic subsystem symmetries, which depend on the geometry of the underlying lattice. And it has extensive ground state degeneracy, which grows exponentially with the number of the lattice sites. Okay, and since and fractons have been studied in various contexts, from quantum information perspective, there's some hope to harness the immobility of fractons for robust quantum information storage. Then we have thermalization. So in those fractal models, thermalization is typically slower, or in some cases, it may even be evaded entirely, leading to many-body localization, fragmentation of the Hilbert space, and so on. Then we have topological order. So as I have mentioned, extensive ground state degeneracy, that doesn't really fall into the typical topological order that we are familiar with. And yeah, and then we have elasticity. This is really something very interesting that I will not really talk in this talk. However, those fractons are related to higher rank gauge theories, and those higher rank gauge theories, they can provide a dual description of low energy of elasticity. And in particular, in this duality, the role of the fractons is played by the topological defects. Okay, and then we have gravity. So linearized gravity in particular, the theory of linearized gravity very closely resembles this higher rank gauge theories. And finally, we have another very interesting topic that I will not cover today, really. However, Christian will tell us more about that tomorrow, actually, is the quantum field theory. So if we come back to this X-cube model, it has local interaction. And typically, we would hope that if we have some lattice model with local interaction, presumably, we should be able to obtain some sort of long distance description in terms of a continuum effective field theory. However, in this case, it's not so clear how to do that, given the peculiarities that I have mentioned, namely those excitations of restricted mobility, subsystem symmetries, and extensive ground state degeneracy. Okay, and fractons can be realized in a very simple way, just by imposing the dipole symmetry. So what we mean by that is, if we just imagine an ensemble of charged particles, the total charge of the system may be conserved. And on top of that, we demand that also the total dipole moment of the system is conserved. And, oh, sorry about that. I hope it will not be doing that all the time. But yeah, and so if we do that, then an isolated charge is a fracton because it cannot move. Because, I mean, the dipole is just the position times the charge. So if an individual charge moves, that changes the dipole moment. That's not really allowed by the symmetry. However, there is some dynamics that can happen. For example, charges can form like a bound state, and then they can move together. For example, if they form a dipole. And there is some other dynamics that can happen also in those systems. And somehow the focus on this talk is really to try to obtain low energy description of these many-body systems that have this dipole symmetry. Okay, and since I'm speaking to like a sort of like a high energy audience, I think I can say that, then let's just consider very quickly what does a field theory with dipole conservation look like. So we have, so if we want to, for the total charge and the total dipole moment to be conserved, we demand invariance under the linear shift. So this is not just a constant shift, but it depends linearly on the coordinate. And in other words, you can check that for this transformation, the nether charge is the total dipole moment and the total charge. Okay, so this transformation incorporates dipole conservation. Now we can, what we do, we just define an operator that transforms covariantly. We can construct the Lagrangian. And typically this covariant operator may just be a derivative of the field, transforms covariantly. In this case, with a little bit of thought, you can convince yourself that the lowest order, least amount of derivatives, least amount of instances of the field object that you can construct is actually this operator right here that is quadratic in the field and has 2 derivatives. And then you can construct a Lagrangian, and it takes the following form as shown here. And funny thing about this Lagrangian is that it is non-Gaussian. It is missing this partial I phi square kind of term. And on top of that, it's strongly correlated. It has this quartic interaction. And the problem with this such a Lagrangian is if you would like to perform some sort of perturbative computations, then it's not really so clear how to do that. Or at least I wouldn't really know how to do that. And somehow that was also a motivation for the study that, okay, we have this Lagrangian, strongly correlated, non-Gaussian, but hydrodynamics doesn't care about none of that. Hydrodynamics just cares about the symmetries, and the symmetries we know. And then we can also have a p-wave superfluid, which also Jay has mentioned in his talk already, where the dipole symmetry is broken spontaneously. And then we have this dipole Goldstone that nonlinearly realizes dipole symmetry. And the zero energy effective Goldstone description is just this weakly coupled sigma model. Because if you go to the Fourier space, you don't have the k-square. Yeah. So what I mean, Gaussian. So yeah. So you don't have the spatial derivative square. So yeah, so if you try to do the path integral formalism, you would like to have Gaussian integrals, right? Otherwise, we don't know how to integrate. Yeah. Of course, that's right. You can try to perturb around that sort of. I would call it like a trivial theory, but then actually you run into problems. And I think Kristen will explain that tomorrow, actually, so I will not say more about that. Yeah, okay. And so we can have this P wave, which is just this description. We can also have an S wave when the monopole symmetry is also broken. In that case, we have an additional scalar Goldstone that now nonlinearly realizes both the monopole and the dipole symmetry. And yeah, so these are the possible symmetry breaking patterns. Well, not all of them, but the ones that we focus on this talk is construct hydrodynamics for the P wave and for the S wave. Well, actually, we initially wanted to describe hydrodynamics for the unbroken phase. And in doing so, actually, I will explain you what I mean by that, but we ended up describing P wave somehow without even knowing that. And I will explain you how that has happened. But okay, so let me review hydrodynamics. Jay has already provided a wonderful review of hydrodynamics, but here we take somehow a different perspective. And so hydrodynamics is an effective field theory when the IR variables are the conserved densities. And the hydrodynamic equations are the conservation equations. And what we would like to do in hydrodynamics is we would like to solve these equations and to determine the evolution of the conserved densities. So for example, here I am showing you a translationally invariant system that conserves charge. And then what we have to do is in hydrodynamics, we would like to express those currents in terms of the densities and organize in a perturbative expansion in the derivatives, so that we can then solve the equations order by order in the derivatives. And so how does it work in practice? Is very simple. So we define the entropy density. Whatever the entropy density is, it has to be the function of the conserved densities, because that's the only variables that we have at our disposal. And then we can introduce those conjugate quantities, temperature, chemical potential, velocity. So by the way, here I am somehow working like in the microcanonical ensemble. Whereas in J talk, he was working in the grand canonical ensemble. So for me, really, the fundamental variables are the densities that are well defined microscopically. And those velocity and chemical potentials is just some notation for just partial derivatives of entropy. Okay? And and those expressions for those currents are not arbitrary. They have to satisfy certain phenomenological requirements. For example, the second law of thermodynamics. And actually, the second law of thermodynamics, as I will argue right now, is it fixes exactly the form of the constitutive relations. The constitutive relations are those expressions for the currents. And so with some algebraic manipulations, after defining the entropy current in this way, you can arrive at this expression. And now, well, we also introduce this pressure. And now we will demand that this has to be greater or equal than 0, which is basically mean we impose the second law of thermodynamics locally, such that locally the second law works. And this exactly fixes the form of the constitutive relations. So, so if you think about it, it has to be greater or equal to 0, so it has to be semi-positive for arbitrary configurations of fluid variables. So if we look at the 0th order currents without any derivatives, the only way to guarantee that is if all the brackets vanish simultaneously. And that precisely gives you the 0th order hydrodynamics. And then you can see that the 0th order hydrodynamics is non-dissipative because the production of the entropy will just be 0 in this case. You can carry this analysis further and find the first order constitutive relations. And then you can convince yourself, if you plug these constitutive relations with those transport coefficients, that I have introduced 5 transport coefficients that satisfy these inequalities, if you plug them into this equation, what will show up is just going to be like a semi-positive quadratic form. So, so those are the most general constitutive relations that satisfy the second law of thermodynamics. And then we can compute of course, now we plug the currents back into the equations, and we solve the equations. The equations are nonlinear, so we don't really solve them. What we do is we just linearize, and we can find the modes. And we just found the mode, so we just found the sound mode, shear mode, and the diffusive mode. And for the people that is bored, I may have like a little question. So why is there 5 transport coefficients, whereas we know that in hydrodynamics, there should just be 3? So I leave this question out there. If somebody wants to answer at some point, then feel free to do that. Okay, now let's talk about dipole conservation a little bit more. So now, what are the local equations that guarantee, in other words, what are the word identities corresponding to the dipole symmetry? So if we want for those, this is just in terms of the continuum mechanics. So it's not even, we don't make any reference to any action. We just have those charges, which are those integrals. And oh, by the way, so the dipole moment here, you can see is defined, it has 2 contributions actually. It has this, what I call an orbital contribution, which is charge times the position, but I also have this pi I, which is intrinsic dipole density. So here I am allowing for intrinsic dipole density, and you can understand it by just, by analogy to spin. So if you have angular momentum has an orbital contribution, and may also have a spin contribution, which is intrinsic angular momentum. And here we are allowing for the same thing, for this more general scenario. And you can convince yourself that if those local equations are satisfied, those integrals, when you take time derivative, they just give you a boundary term. So those are the local equations for conservation of charge and dipole. And if you look at those equations, the first equation has a form of a conservation equation, but the second one does not, because on the right-hand side, it has a source. Yes? Yeah, one such a theory is this theory. This theory has intrinsic dipole. That are linearly realized. Yeah. Some sort of fermions. Yeah, I mean, yeah, that's a good question that I don't know the answer. I mean, you can, yeah, I don't think that this was done, but that's a good question to think about. Yeah. I think the answer is yes, but I don't know the theory. Okay. Right, where were we? Here. So the second equation is not really a conservation equation. It has a source. And if you in a sort of, if you find out the modes, I mean, this mode corresponding to pi I basically is gapped. And in the hydrodynamic limit, if you consider long times, basically the evolution of this intrinsic dipole stops, and the charge current is just given as a total gradient. And in that case, in this long time limit, you just have a single equation that is this hallmark of dipole conservation that also Jay was introducing in his talk. And then, okay, it has actually been, you may be wondering, okay, it's a bit abstract, this whole discussion about dipole symmetry. Nothing conserves dipole, right? Actually, there was an experiment in tilted Fermi-Hubbard chains in cold atoms when they actually were able to have an emergent conservation of dipole moment and I can tell you more about that if you're interested, but basically they found this subdiffusive relaxation of the charge density modulations, and this precisely if you try to solve this equation by applying hydrodynamics, what you will find is this subdiffusive relaxation. So in normal hydrodynamics with just charge conservation, you have a fixed law for the transport of charge. Here you will have an equation with 4 spatial derivatives of density that gives you the subdiffusive relaxation that has been observed experimentally in those experiments on cold atoms. Okay, so let's summarize our symmetries and conservation laws and that we will incorporate in the hydrodynamics. So we have translations in time and space and the respective conservation of energy and momentum. We have rotations. So if you have rotational invariance, that means we can always improve the stress tensor to make it symmetric. And similarly, we have the conservation of charge and dipole that we have already discussed, that in the hydrodynamic regime, it just means that the charge current will be a total gradient of some tensor current. Okay, now there is something very interesting about this, the algebra of these generators is that the dipole does not commute with the momentum, and the central charge is the charge. And you can understand it intuitively. If you have a charge, you translate it, that changes the dipole moment. So clearly dipole moment is charge under momentum. In the reciprocal way, I mean, dipole transformation is basically a shift in the momentum space. So that's how momentum is charged under dipole. And so that means, by the way, this is of course perfectly analogous to the Carroll algebra. When the Carroll boost does not commute with the momentum, it gives you the Hamiltonian. It's just that here the central element is the charge. So the momentum transforms under charge. What does it mean for the hydrodynamics is that the momentum density will not be invariant. Momentum density transforms in this way. And also the stress tensor has to transform such that the momentum conservation is covariant. And so we see that this combination momentum per charge has a shift symmetry, just like a Goldstone would. Okay, so we just keep it at the back of our minds for a moment. And then if we would like to construct an entropy density function for this dipole conserving systems, we cannot, so entropy density has to be consistent with the symmetries. For example, if your system is rotationally invariant, your entropy density will depend on the momentum square, right? In other words, the velocity will be proportional to the momentum. And here we would like to incorporate this dipole symmetry, which means the entropy cannot depend on the momentum directly because that would not be invariant. And the only way, and to construct an invariant quantity, we kind of take an analogy to the superfluid. Since this quantity transforms like a Goldstone, we just treat it as such, and we postulate that the entropy depends on the derivative of that quantity, because the derivative of that quantity is the lowest order structure that you can construct that is invariant. And then we have this fractonic version of the first law when we introduce this quantity Fij that is conjugate to Vij, which is just some thermodynamic quantity that is specifying the equilibrium state. Okay, so instead of having velocity and momentum, we have this tensorial structure here. And hydrodynamic equations, I remind you, are just those ones. So energy, momentum, and this generalized continuity equation. Okay, now we can do hydrodynamics in an analogous way like we did for this normal conventional fluids. And what we will find is, so this is the leading order hydrodynamics. And here I define this quantity that I called an effective velocity, which is, as you can see, is defined as a gradient of F over N. And F is a thermodynamic quantity. But V is a gradient of that. So in other words, V, this effective velocity, is an out of equilibrium quantity. It is 0 at equilibrium. Okay, and you can see that if you look at the constitutive relations, they resemble very closely the conventional hydrodynamics, but the velocity is defined in this peculiar way. So, and what that means, basically velocity is order one quantity, because it has a derivative of F. And if so, what that means is that since velocity is order 1, that means that in the energy current, you have to be consistent, to have a consistent derivative expansion, you have to introduce this term, which is the thermal conductivity, comes with the gradient of the temperature. You have to introduce this term because it's the same order in the derivative expansion. And what that means is that the leading order hydrodynamics of those fluids is already dissipative. Okay, so those fluids, in a sense, are strongly dissipative. And if we can carry this analysis to the next order and we find 12 transport coefficients, that the constitutive relations are not so illuminating. And then we can compute the hydrodynamic modes. And so we find, instead of having like a sound-like modes, we find this mode that is magnon-like. So you can see that it goes like k squared. And then it is attenuating diffusively. So this mode is somehow strongly dissipative in a sense that the dissipation and propagation come at the same power of momenta. And we have this standard diffusive mode. And somehow, interestingly, the shear mode is subdiffusive, starts at k to the 4. So these are like the differences to the conventional hydrodynamics. And now let me come back to this point about, so here we try to describe the unbroken phase. Yes, there's a question? Yeah, so here we count time derivatives as two spatial derivatives, that's right. Yes, that's a good point. So I think what Christian means is that those k to the squares, they come from the sort of zeroth order, whereas to get this k to the 4, you have to go to the next to leading order. So in other words, these constitutive iterations have just 0 here. But if you go to the next order, you start having k to the 4 corrections, which I am not writing really here, and then you have this shear mode not being at 0. That's right. Okay, and now, okay, so here we presumably describe the unbroken phase, because I haven't introduced any Goldstones. I haven't told you that some symmetry is broken or none of that, right? But so let's see, okay, so now let's try to describe the P-wave phase. Okay, the dipole Goldstone transforms has a shift symmetry. Now we can construct this entropy, the invariant combination. Now we can construct invariant combination with momentum and the Goldstone, because they both transform non-linearly. And this is what the entropy is gonna look like. And we have this also this superfluid velocity gradient of psi kind of term. So in other words, this is just a generalization of this zero temperature Lagrangian that I showed you at the beginning to the finite temperature. Okay, and then, however, if we do hydrodynamics, what we will actually find is that the dipole Goldstone is not independent from the momentum. And in particular, dipole Goldstone is just given by the momentum per charge, up to the derivative corrections. And so what that means is that you can integrate out the dipole Goldstone, and you then get this effective description, which is precisely what we have just done what we have just described. So in other words, what we have described in those previous slides that I have shown you was not the unbroken phase, it was the P-wave phase, really. And this has somehow been explained by this by these groups, which some of them are actually here. And basically, this all fall into this simple physical observation that a thermal state at finite density that travels with a finite velocity, it breaks the dipole symmetry. Because if there is transport of charge, finite velocity, that breaks the symmetry. Okay, so what we have this, so in general, the dipole symmetry will be broken. Okay, now we may try to describe the S wave. So I remind you of the Lagrangian. Lagrangian has this form. You can derive it from coset constructions, for example, or whatever other method you would like to use. And we can define those superfluid velocities. VIS and Xij are defined in this way. And then we would like to generalize this to finite temperature to be able to do hydrodynamics. And the invariant momentum that we can define here is this P tilde quantity. So if you look at this quantity, it has those contributions from the total momentum density, which is Pi, and then those other two contributions, this is just the momentum of the Goldstones. If you look at this, for example, this n gradient of theta term, that is just the momentum of the theta Goldstone, right? And this other pi gradient psi term is just the momentum of the dipole Goldstone. So we define this momentum, and we understand this momentum as thermal momentum. It doesn't carry any charge, neither dipole nor charge. It is neutral, and it is invariant, and therefore our entropy can depend on that quantity. So in total, our entropy depends on VIS, Xij, and P tilde. So it has an interpretation of a free fluid model. We have free components that can all flow independently of each other. They may exchange momenta, and the hydrodynamic equations are just those ones. And just now we have to, on top of the, now I am, you can see that I am reverting to this equations with intrinsic dipole, because as I have mentioned, this theory has intrinsic dipole. So yeah, and I am supplementing the conservation equations with the so-called Josephson relations, which basically determine the dynamics of the Goldstones. Yes. Yeah, so it's a good question. So that's how, so you define the, you can define the Hamiltonian, you define the Poisson bracket structure, which follows just from the symmetries. I mean, it looks long, but it's very simple. It's just telling you how things, it's just symmetry-based arguments. And from that, you can literally compute the Poisson bracket. So you take theta dot is a Poisson bracket of theta with h, you get the Josephson relation. Yeah. Here? No, finite temperature, but non-dissipative. Just Hamiltonian formalism. So here I assume. Of course. Yeah. Right. This is backup slides, so this is just to answer the question. But in the same way, you're using equilibrium partition function, but your system will be dissipative. But still, you can categorize the non-dissipative transport by using that tool, and later on you will introduce dissipation. So that's what I'm doing here. I'm just the ideal transport I can find with this method. The dissipative transport I find with a different method, with the entropy current formalism. Yeah. And here with this bracket, you can check that this p tilde momentum is neutral. But coming back to what we had over here. So the Josephson relations are derived from the Hamiltonian formalism. Of course, those Josephson relations admit arbitrary derivative corrections that I should basically have some sort of placeholder for that here. And now we take the hydrodynamic limit. So actually this theory has massive modes, and we can integrate them out. How we do this in practice is that this equation for pi I, intrinsic dipole, and this equation for the superfluid velocity VIS schematically takes this form. And if you look at it, if you go into, so beta and gamma is just some transport coefficients. And psi is just some thermodynamic, just some susceptibilities. And if you look, if you're in the hydrodynamic regime, you can basically get rid of the time derivatives because they are small compared to the other term. So in other words, you can just delete the time derivatives in those equations, delete the time derivatives. And in turn, this implies, again, charge current is a total gradient of some tensor current, and the dipole Goldstone, this is like an inverse Higgs constraint. This is basically an inverse Higgs constraint that the dipole Goldstone is just equal to the gradient of the theta of the scalar Goldstone. And then we just end up with 4 dynamical equations, which are the same equations we had before, but now we have this scalar Goldstone that has this respects this Josephson relation, and here I have added mu d for arbitrary dissipative corrections. And we can, again, do hydrodynamics, find the modes, and what we find in this case is we find the sound mode. So now we have a sound mode. Why is that? Because we have this p tilde quantity, this momentum of thermal excitations, and those thermal excitations, they carry momentum and they carry energy, and they are responsible for this sound. So this eigenfrequency is associated to the eigenvector that is related to just momentum and energy. We have this Magnon-like type of mode, which is Magnon-like and has subdiffusive relaxation. That's not really something that you see in a Landau superfluid, for example. And we have the shear mode, which is just k square, which is again carried by the thermal excitations. So the only difference between this spectrum and the spectrum of the sort of vanilla Landau-Tisha two-fluid model of superfluid helium is just that the second sound, the second sound is not a sound really, but is magnonic. So it has this k square and subdiffusive attenuation. Okay, and so now let me summarize what we have done. So we have constructed a low energy description of fracton superfluids, dipole conservation, using the framework of hydrodynamics. And what we have found is that in the P wave, we had Magnon-like propagation of sound, and we have dissipation already at the lowest order. And when we had a subdiffusive shear mode. In the S wave, we basically found that the second sound was not the sound, but it had a Magnon-like dispersion relations. And we can summarize those findings in a single sentence that kinetic constraints, such as dipole conservation, lead to a slowdown of the collective macroscopic dynamics. And future directions, we can think of some physical realizations. So as I mentioned, in relation to elasticity, so a valid question is how to modify this hydrodynamic theory to actually describe, for example, the hydrodynamics of topological defects. And similarly, the relation to tilted chains that I mentioned, superfluid vortex crystals, we are now working to understand basically physical. So far, this construction has been very abstract. I postulated some symmetries, I derived hydrodynamics. But now we are just working to try to make connected to the physical systems. And finally, you can consider different space-time symmetries. So higher multipole symmetries, like a quadrupole symmetry, for example, this might be relevant to elasticity, and maybe even subsystem symmetries you can incorporate. And finally, you could also think of incorporating Carrollian symmetry, like, for example, Jay did in his work. Okay, so with that, I thank you for attention, and